So when we do labs in chemistry, we often use Bunsen burners as a heat source. What is a Bunsen burner doing? Well, it's burning methane, which is natural gas. If you have a gas furnace or a gas stove in your home, it's using this chemical and it's reacting it with oxygen. So when we write a chemical reaction, we start by writing our reactants, and we can have any number of reactants going on here. So let's label these reactants. And then what's going to happen is there's going to be some process that happens that causes some kind of fundamental change to these molecules. And we've generalized that process with an arrow, just a straightforward arrow. Now, this could be heat, this could be a spark, this could be an electrical impulse, this could be just mixing. There are reactions that happen just by two fluids mixing together. And so in this case, we're going to start this by adding a little bit of heat, right? We just have to add a flame or a spark, and suddenly the methane will light on fire in the presence of oxygen. If we wanted to put it out, we could just remove the oxygen and we'd be done. Once we go through this reaction, what does this produce? Well, these chemicals, these molecules are going to rearrange to form CO2, carbon dioxide, and water, H2O. This is going to be a gas, this is going to be a gas, all of these are gases. So we have, all of these are gases, we're just going to heat them, and it's going to cause the methane to burn, producing carbon dioxide and H2O. So we call these on the other side, we call these our products. These are the products of the reaction. And you can kind of think of this like baking, right? This could be your flour and sugar and, I don't know, baking soda, eggs, whatever. And you mix them all together and then you heat them up and out comes a cake or cookies or something. So you've got ingredients and you've got your final product. In chemistry, we call these reactants. We call our ingredients reactants because they are going to react together. And when we get these products, our reactants are gone. So at the product side, these have been used up. And so what we're having here is a fundamental change. Across this arrow, we have a chemical change occurring where these bonds are reorganizing themselves. So let's draw the Lewis dot diagrams here to help us understand what we need to do with reactions. Okay, so I've got my reactants drawn on the left side, my products drawn on the right side. This dotted line represents the passage of time. So on one side of this is one situation, on the right side of this is another situation. They aren't mixing. So what I should notice here is I have a different number of these atoms, right? Over here, I've got 3 oxygens. Over here, I only have 2. Where did this third oxygen come from? What is happening here? Well, in order to get this to be right, to get this to be working, to conform to reality, we have to follow a principle called the conservation of matter. The conservation of matter is going to state that in any chemical reaction, the reactants that I start with are going to be conserved. That means I'm not going to gain or lose any atoms throughout this. They're just going to rearrange. What that means is when I react these, I'm not going to get an even 1-to-1 ratio, right? I'm not going to get a clean 1-to-1. I'm going to get a specific ratio. And as chemists, we need to figure out what that ratio is in many reactions. And so this is going to be one of the first skills that we're going to learn in our reactions unit. We need to be able to balance these. And so if I look here, I'm going to keep track of how many of each type of atom I have. Combustion reactions, that's what this is, are nice and simple to keep track of because at the end of the day, it's just going to be a carbon. Let's do this in let's do some purple. Got carbon, got hydrogen, got an oxygen. Okay? So how many carbons do I have on each side? Well, on the left side, I've got 1. And I can see that I've got 1 carbon right here. On the right side, I've got 1 carbon right here. I've got 1. How many hydrogens do I have? On the left side, my starting side, I've got 4. On the right side, I have 2. Okay? And oxygens. How many do I have on the left side? Well, I've got 2. I've got 2 in that O2. And then on the right side, I've got 3. And so I need to figure out how many of these molecules am I going to create and how many do I need to bring? It's like for every 1 cup of sugar, do I use 1 cup of flour or 2 cups of flour? That's what we're trying to figure out here. Now, I can't change these molecules. I can't just go, oh, I need 3 oxygens. We'll just get rid of this and make that a 3. Because that would fundamentally change this molecule. Because O2, that's oxygen we can breathe. O3, that's ozone, and that will poison you. So we can't just change that molecule. I can only bring more or less of it. That's what I'm trying to show with these Lewis-Dot diagrams. So first off, let's start with the hydrogen. My carbons are already balanced, so I don't need to do anything with those. But the hydrogens, I've got 4 on the left side, 2 on the right side. So I need 4 hydrogens on the right side as well. And so how would I do that? Well, what that means is this reaction is actually going to produce 2 waters. It's not just going to give me like a couple hydrogens on the outside. They're not just going to be sitting there by themselves. They're always going to come in this molecule. So if I want to get more hydrogens, I need to bring more waters. So now I've got 4 hydrogens, right? And that means I brought 2 H2O. Okay? Now, I'm going to scribble this out, put 4. So I've got my hydrogens balanced now, and now my oxygens. How many oxygens do I have now? Well, I've got 1 and 2 from the CO2, and I've got 1, 2 from the H2O. So now I've got 4. I've got 4 oxygens on the right side. Okay? So now I need to balance my oxygens on the left side. That should be pretty straightforward. I'm just going to bring another O2 molecule. Great. So it means I'm bringing 2 O2. Now this becomes 4. And now my reaction is balanced. Now I have the same number of each atom on the left side as I do on the right side. And that's my goal here. I need that conservation of matter to be perfect. I need the exact right number of atoms. So when we're going through this is important because this is going to relate to like doing actual chemistry. If I want to create something, let's say I wanted to produce a certain amount of heat or needed to produce a certain amount of water out of methane and oxygen. Well, I would need to know how much methane to bring and how much oxygen to bring. And because I'm able to balance this reaction, now I know for every 1 mole of methane I bring, I'm going to need to bring 2 moles of O2. And that can be really important. Because if I didn't have enough O2 in something like a combustion reaction, instead of making CO2, it would make carbon monoxide, which is very poisonous. This is why it's not good to have fires in an enclosed room, because it's going to use up that oxygen and then it's going to start producing carbon monoxide, which is very bad. So it's important to be able to balance these reactions so that we can find this ratio. So let's do a few practice problems.